How training works, like on a very, very high level. This is approximately the amount of data that is used for training and fine-tuning. So on the left, there are like trillions of tokens that are provided in the base LLM as a knowledge base. It's numbers in, numbers out. And this contains of all the general knowledge, all that the foundational model providers have put into the training data set. It's months of compute, just to give you understanding how much energy and information and effort is being spent to train LLM. When some big companies, foundational providers, train the LLMs, they have to align the training schedule with the power grid providers and power plants, because if they just do it without control, they would put all the electricity network down. The impact is just immense, and it takes times, months and months of compute to train kind of large language model with this amount of tokens and data set, and a lot of energy. So kind of with energy to train, like, I think even 1-year-old LLM about 600 billion tokens is enough to go to the moon and back 500 times. So it's like really immense. And this takes a lot of effort, but this gives this foundational model that trained on all the average approximation of all the knowledge ever available on the internet that companies were able to build a data set from. And then there goes the fine-tuning process. And fine-tuning process is the approach when you specify explicitly how to align the outputs from this general corpus of data for particular outcomes. You can specify for the domain, for the style, for the particular ethics, for like guardrails, constraints, anything that you would want your AI to be fine-tuned for. And so kind of the fine-tuning is much more affordable process. And for many use cases, for example, very often when for the companies and the consumers, when your prompts become like too big and too large, and you still see some deviations and you have to constantly add some additional rules and guardrails, very often it might make sense to find someone to help to fine-tune a particular LLM for your general purposes. And that's usually much more affordable process. And now we have a lot of infrastructure for it. So what you need to know, if your use case, you have to constantly do some adjustment of your inputs and have still some deviations from what you'd expect, and you have a well-defined understanding what it is that you're missing in the outputs, you can always fine-tune some available general purpose LLM for your purposes. And that's how kind of it makes a lot of difference. So whenever the general rule of thumb, whenever prompt tuning stops working, it's kind of time to think about how to turn on and do the fine tuning. Okay, let me move on to the next. So how training differs from inference? So training is a process when you collect all the data set inputs, outputs, combination pairs, and build this huge mathematical calculator that is able to predict next words or next like most likely outcome of your request. So, and fine-tuning is being able to specify how exactly to process. And this is training. The process that most commonly you will be using is called inference. And inference is extracting most probable outcome based on your input provider. And how this usually works, now you understand the token, you understand the model, you build your prompt, provide it to the system tokenizes it, breaks it down into like particular token, sequence of number. Model processes your request. It predicts what will be the most likely response based on its training data set. generates output tokens. Output tokens get converted into text that you receive in your response. So, and that's where kind of the size of the model and the performance matters, because, for example, some requests to smaller models can take less than a second for inference, but more complex models, it can take tens of seconds or even like minutes, like in case of reasoning models, for example. So that's when models self-reflects on its own response and tries to process the same request again and again. Again, the output matches particular criteria. So that's where the outcomes are kind of meta, and you need to think like very well strategically how to choose the right model for your parts of the process. Why I'm explaining this now? Because for some tasks, for example, deep analysis or like synthesis of several research results, using expensive model makes sense. But for some more fine-tuned agentic processes like collection of data, a recombination of already known and existed that doesn't require deep analysis or deep understanding, you can just use like a smaller model and you won't lose a lot in the value of the information that you get. Because these smaller models are very often excel at pretty cognitive expensive tasks, but they don't cost as much and they don't take as much time. It's kind of the analogy that I like to give is in avionics. It's been for quite a while that pilots have been offsetting their decision making to our cognitive offload systems. It's basically some auxiliary systems on plane that help to make them decisions faster and they make decisions for them. So they don't have to think of all details on how to balance the angles of different controls on the plane. It's all kind of done automatically. It's offloaded from the pilot's decision-making system. They don't have to think about it. And similarly, for us, like now with AI, these systems can be used as these cognitive offload structures and systems that just let you focus on the direction and trust your autopilot to handle the rest of the cognitive load on yourself.